This is chapter 6.1, part 2. And we left off talking about polygons, and let's proceed forward. And the question is it a polygon? This is in reference to your book here. And if you look in your book, for chapter 6.1, you'll find these images here. The question is it a polygon? Okay? Remember, each segment has to connect to another segment. So, here is one end of this. This is A, B. This segment is called AB on this triangle. Does this endpoint A connect to another line segment? The answer is yes, it does. Right with this segment there. Also, does the endpoint B connect to another segment? And the answer to that is also yes, it connects right here to that segment on the star. So is this a polygon? Yes, it is a polygon. Right? How many sides on there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. So what do you call a 10-sided polygon? Okay? And that's going to be a decagon. So this will be called a decagon, even though it's a star. Next here we have example 2. Is this a polygon? It looks like a yes to me because for this segment here at the bottom, and I'll call that CM. Does endpoint C, connect to another segment? Boom, 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 and it does. This one right there. Does endpoint M connect to another segment? It does, right there. Okay, does that happen on all of the segments? The answer is yes. Therefore, this is going to be a polygon. It is how many sides? And I count 1, 2, 3, 4. Again, 1 side, 2 sides, 3 sides, 4 sides. And a 4-sided polygon is called a quadrilateral. Let's look at this here, number 3. Is this a polygon? And the answer to this is no, because one side is not a segment. Okay? Yes, this is a segment, but if this is segment TM, does endpoint T connect to another segment? It connects to something, but this is not connected to a segment. It's kind of like a semicircle, half circle. So this is no. This shape is not a polygon. Okay? Next one. Example 4. Here we have. Is this a polygon? And the answer is no, because some of the sides are going to intersect with one another. Okay? Example 5. Is this a polygon? Yes, even though it's different shape, it is a polygon. And then example 6. Is this a polygon? You should have said no, because 2 of the sides only intersect one another. They have to intersect at 2 other sides. So for example, if I look at this segment here, and I call that AM, does segment A connect to another endpoint or another segment, The answer is no. What about M? Yes, it does. It connects to this segment there. However, A doesn't, so this is not a polygon. Also, you could have looked at it here. This segment, if I call that TZ, does T connect to another segment? Yes, it does, right here, this segment there. Does Z connect to another segment? No, it's open-ended, so again, it's still not a polygon. Moving further. All right, convex and concave. What is convex and concave? Simply, convex means when a polygon has line segments. If I were to extend them out, does it run into the another side of the polygon? So, for example, this quadrilateral, remember 4-sided, 1, 2, 3, 4 sides is called a quadrilateral. This 4-sided quadrilateral, if I were to extend the sides, so I see this segment here. If I were to extend it out, does it run into another side that's on this particular polygon? That one does not. If I were to intersect this side here, if I were to extend it, does it run into another side on there? It does not. Let's check this bottom segment. If I were to extend it, does it run into on the interior there? No, it does not. And then finally, if I were to extend this one here, do they run inside? No. So this is called convex. The other side of that is non-convex, or you'll probably hear me say concave in other words, but they mean the same, concave or non-convex. This is when a polygon has at least one segment. If I were to extend it, it's going to intersect with another side of the polygon. So what does that mean here? Okay? Let me hit delete that. Alright, so here it is. Concave or non-convex. This is a 1, 2, 3, 4, 5, 6, looks like a 7-sided polygon here. So we're going to have what we call a heptagon here. Heptagon with the P. And if I look at this particular polygon here, the question is it concave or convex? Well, this one, if we extend the lines. So if I look at this segment here, if I were to extend that line, does it run into another side? The answer is no. If I were to extend this particular segment, does it run in inside? No. If I were to extend this particular segment, oh, it runs into this side over here. Again, if I extend this segment, it runs into this other segment side there. Therefore, because it will run into another side, it is called concave or non-convex. And I can even look at this other segment here. This segment, if I were to extend it, boom, it runs into this other segment. So again, in at least two places, it's going to run into another segment. If we were to extend it into eternity, then that's going to be concave. Some other information. Equilateral polygons. You should remember what equilateral. Equal, same length. Polygons, many-sided shapes. Okay? Equilateral polygons, and I'm going to hide this because some of you get the writing. It should be scrolling. There we go. There it is. It's just moving slow. Alright. Equilateral polygons have all congruent sides. So if it's 6-sided, if it's a hexagon or a heptagon, all of the 6 sides or 7 sides are congruent. Equal angular. Equal angular polygons means all the inside angles are congruent. So if this were equal angular, that means that this angle here is equal to that angle, is equal to that angle, is equal to that angle, and that angle, that angle. All the angles on the inside will be congruent. And this angle here. Okay? In this particular case, we know that that's not equal angular. Okay? You can have equal angular. It can be an equal angular square, equilateral triangle, equal angle quadrilateral. Any polygon, depending, well, I shouldn't say all, but polygons that have all interior angles that are congruent are called equal angular. Their inside angles are or will be congruent. Equilateral, again, means that all of their lengths will be the same. That means if this were equilateral, that means if this is 8, this short one would be 8, that long would be 8, that would be 8, that would be 8, that would be 8, that would be 8. All of the side lengths on equilateral, remember lateral, the length, will be congruent. Doesn't necessarily mean length, but here I'm calling it so. A regular polygon means when both occur, equilateral and equal angular. So regular polygons mean that polygon is both equilateral and equal angular. Theorem 6.1. Interior angles of a quadrilateral. Remember, that's the 4-sided shape. Come on. Remember, for triangles, the interior three angles equal 180 degrees. Well, there's a special rule for quadrilaterals. And a special rule is the interior angles of a quadrilateral. That means that all interior angles on a quadrilateral must equal 360 degrees. Okay? Again. All right, remember, again, triangles with interiors were 180 degrees. We were able to figure out this measure, and that final measure. It had to equal 180 degrees. Well, on a quadrilateral, when I have a rectangle, square, even if it's odd shaped like this here, the interior angles must equal 360 degrees. So if this is angle 1, that's 2, 3, 4. Angle 1 plus angle 2 plus angle 3 plus angle 4. All 4 of these interior angles must equal 360 degrees. It doesn't matter if it's an odd-shaped quadrilateral. This angle, plus that angle, and I'm going to give them numbers, 1, 2, 3, 4. Pretend that's 4 there. So angle 1 plus angle 2 plus angle 3 plus angle 4, doesn't matter the shape of the quadrilateral, okay? Or all 4 interior angles must equal 360 degrees. Okay? Diagonals. Okay? What a diagonal is. If I have this particular shape, come on, my board's moving slow now. If I have this quadrilateral here, I'm going to roll that up just a little bit. Come on. If I have quadrilateral A, B, C, D, remember I named it, they have to go in consecutive order. I could not say A, C, B, D. I called it A, B, C, D, or I could have called it C, D, A, B, whatever. But anyhow, this particular quadrilateral, what I want to look at is a diagonal. A diagonal is a line segment that joins 2 non-consecutive vertices. What does non-consecutive? You have to know what consecutive means. Consecutive means next to. Well, I'm saying that B and D are non-consecutive. So if I were to connect these two, that means B could go to D, and that's a diagonal. What's another diagonal that's potentially there? A and C. That's also a diagonal. AC is a diagonal. Just like DB is a diagonal. I'm joining 2 non-consecutive vertices. They don't touch one another. Okay? Can I join C to D? No, because C is right next to D. So that's actually consecutive, not non-consecutive. So CD does not work. I believe I have another one over here for us. Come on, computer. Ah, here's one. This is the one I want. Let's look at this next quadrilateral. M, N, O, P, Q. And let's draw some diagonals. Remember, it means non-consecutive. So if I come over here to draw non-consecutive, what does that mean? Can I draw from M to N? The answer is no, because these are consecutive or next to one another. So that's a no. That's not a diagonal. What about MO? Yes, that is a diagonal because they are not next to one another. That is a diagonal, theoretically. And then QO, yes, that would be a diagonal. QP is not because they're next to one another. Hopefully you get what I mean. And quadrilaterals, just like a triangle, they have both interior and exterior. Remember, inside and outside angles. All right. Quadrilaterals, when cut by a diagonal, form 2 triangles whose measures have to be what? 180 degrees. So here's another quadrilateral. Let me see if I can grab and move this down here. If I take this quadrilateral, when I cut a quadrilateral by a diagonal, such that I'm getting ready to do here. So here's my diagonal. What shapes do I form? I form two triangles. Here's my first triangle, and here's my second triangle. Okay? Here's a question for you, and I'm going to go back here. What's the interior angle measures of a quadrilateral supposed to be equal to? And it's 360 degrees, right? Okay? Now, if the interior is 360 degrees, watch what happens. I'm going to go back to what happens when you cut a quadrilateral by a diagonal. If I cut it by a diagonal and I form two triangles, here's my first triangle. Oopsie. And here's my second triangle. When I form two triangles, what's the interior measure of a triangle supposed to equal? You remember, it's 180 degrees. This second triangle is also 180 degrees. If you add 180 plus 180, you will get 360 degrees, which is the measure of a quadrilateral. And there's your chapter 6 lesson, 6-1.